Thank you all very much for being here today and sharing this very special moment with me. I'm extremely excited to tell you what I've been doing in the past 4 years. So here we go. Explaining artificial intelligence with tailored interactive visualizations. I know that title is quite a mouthful, so I thought it was a good idea to break this down and have a look at the most important concepts here. So first, I'll tell you a bit about what artificial intelligence is actually, what I mean with that. Then I'll talk about how we need to explain specific AI models. Then how we need to tailor those explanations. And finally, I will show you all the work I did on interactive visualizations to explain artificial intelligence. During my talk, I will also have two co-hosts. So this is Mr. Brain, and he will have the important job of doing the important tough bits. And there is also Cherry, who will add cuteness to the presentation, which I guess is also important. So let's start with artificial intelligence. I'm sure we've all heard about artificial intelligence. I always compare an AI model with a coffee machine. So you just put something in, and something comes out after it does something. So this is exactly what an AI model is doing, and there's all sorts of AI models that can work for all sorts of inputs and can do all sorts of things. So for example, we can have an AI model that takes into account specific items, and then it will recommend specific items. And this is called a recommender system. For example, take a bunch of tweets, and then here is a tweet that is recommended to me personally, and hilariously, it's about PhDs seeking to leave academia. There's other models, but let me first tell you also such that you know that in the background, these tweets are actually captured as tables. So the system is working with tables of numbers, and the columns are called features. So the number of likes, the number of comments, the number of retweets, etc. So just keep the word feature in mind. Other examples. AI models can also predict the next numbers in the series of numbers, and this is important if you want to get rich on the stock market. There's AI models who can summarize texts. For example, take my PhD text, and then you get this awesome summary. And finally, there's AI models that can also label images. For example, take this very cute guy here, and then you will get the label, well, never mind. The main part here is that there's all sorts of models, and that's why I gave them different colors. And all these models can do one specific thing. So they can classify, they can recommend. But the issue is, as outsiders, we don't know what's going on, right? We don't have a clue why these tweets are being recommended to us. And even for computer scientists, some models are so complex that it's very hard to understand how they obtain specific outcomes. And this is why computer scientists call these AI models often black boxes. And so this black box problem is, well, problematic. Why? Sometimes you just want to know why you get a specific tweet recommended. Or maybe you want to know why you need to invest in a specific share, right? And then there's other issues. For example, these models can make mistakes, such as, just like humans can make mistakes. For example, if they summarize my thesis as the thesis is boring, obviously that's wrong. And I mean, also without the jokes, there are serious issues. Even models from Google classify an image of two people as gorillas, which is not really what we want, right? So the natural question is, how can we open these black box models? How can we get insights in how they work? And I will discuss this question in the next section, which is about... No, it's not about visualizations yet. We will get there, so just hang on there. Let me first explain what explaining means. So this is a bit meta here, but many people, when I talk about explaining, expect, and especially computer scientists, because I talk a lot to computer scientists, they expect that I'm talking about explaining the inner workings of these models. And so this is mathematics, right? And then they are looking for these very important answers to the questions of why does the mathematics actually work out for these models? Or how can these models generalize what they are learning? Or can we prove that they are reliable? But this is not what I will be talking about in this talk. What I will be talking about is so-called reverse engineering. It's a bit of a hard word, but actually it just means that I'm not really looking into the mathematics. I'm more looking into how these models behave, just based on the inputs and the outputs. And then we can answer questions such as, what happens with an output if I just change an input slightly? Or what parts of the input are important to get a specific outcome. Or maybe there are some general rules that the model is following. So this is what I mean with explaining. And computer scientists have developed countless techniques of explainability in this sense. Here you see some: decision trees, decision rules, feature importance, saliency mask, and so on. Now, what's important here is that we can classify these in different ways, and one of them is to which models do they apply. Some of these techniques apply to all kinds of models, and they're called model agnostic. Others are specifically designed for one specific AI model. Those are model specific. And we can also classify them based on their scope. So some explanations give a global explanation. They explain the whole model, whereas others are providing local explanations. So that means they just explain one outcome. And then there's a whole thing in between, model inspection. They allow you to see how the model behaves based on different inputs, different outputs. Okay? So let me just clarify this a bit with some examples. Let's start with decision trees in the case of a global explanation. So let's say we have this black box model that will predict whether you will like a thesis text. We want like a general understanding of this model, and decision trees build trees, and you read them from top to bottom. So you just start with a blue note, number of pages smaller than 100. If the answer is yes, oh, the model predicts you will like the thesis. Yeah, so for my thesis, that doesn't apply, unfortunately. But if you follow, you will see that you will like my thesis because there's lots of images. So, I mean, this is a lot easier, right? You can just follow the tree, and you see what the model is doing. Cool. Another example, feature importance. So think back about the recommended tweets from before. They had different features, right? The comments, the likes, the retweets. And so what feature importance does is it will assign a specific number to all these features, and the higher the number, the more important it is. So in this case, this tweet was recommended to me. Why? Well, topic got a very high number, so probably the model thinks that I find this topic interesting. So okay, I get insights in what the model tells me. Saliency masking. You have this labeled image and you want to know what's important. So you can ask which parts of this image are actually important for this specific label. And since the label here is weirdo, obviously it will highlight the minions, right? So there's all kinds of algorithms that explain algorithms. Cool. One important question, who needs this? And this is not just a silly question in the sense of needing something and why. It's also about the word who. Who implies people? And so I'll be talking about people in the third part. The third part is about Taylor. No, it's not visualizations. We will get there. So Cherry is very excited about visualizations, apparently, but we'll be talking about tailoring. Tailoring, difficult word, but what is that? So far, I've been talking about these black box models as an algorithm. And we've tried to attack these algorithms with more algorithms, like the feature importance and decision trees. But there's also another perspective that we can take, and that is a human-centered perspective. Because in the end, it's about humans. We are using these AI models, and we also need to understand these explanations and work with them. For example, to be better at a specific task, or to better understand the model, or to become more efficient. And the problem is that these algorithmic techniques that I showed you before aren't always that useful in practice. For example, let's take the decision trees from before. Before it was quite easy. You had like 3 things in the decision path. But in practice, these decision trees can become very, very big and very large. And I'm talking about tens or hundreds of decision nodes on the path. So that doesn't really help us as humans. I mean, in theory, it should be clearer, but for us, it's still very hard to keep track of dozens of decision nodes. And another issue is that different people and different contexts require different explainability solutions. I mean, just think about it. If you're not a computer scientist, probably you maybe don't want to understand the whole model, but maybe you're more interested in like specific outcomes. So there's different factors that can influence what you need or what you want or how you can understand something. And one of these aspects is your experience with AI. I mean, there's three kinds of groups in general. We can classify people into AI novices. That means people who have almost no experience with AI, definitely not the mathematics. Those people don't need to know all the mathematics. What they need are tools to be able to trust these models, see whether they can rely on them. Then there's data experts. Data experts are experts in a specific domain, let's say doctors in healthcare. They know their data very well. They need to analyze their data with AI models. So what they need is tools that tune models. They can select different models and see which one is best. And then, of course, there's AI experts. Those are the computer science guys who need all the mathematics and the interpretability and debugging of their models to improve them, right? Now, this classification is quite coarse. I mean, depending on the context, you need different things. Even as an AI novice, there's plenty of explainability solutions that I showed you before. So what we can do instead is we can go and ask people what they need. For example, we can ask questions such as, do you find it interesting to see what the system would predict if a specific instance changes to something else? If the answer is yes, then what you need is a what-if explanation. What happens if something different happens, okay? And then there's all sorts of questions that you can ask people, and based on their answers, you get different explanations. How explanations, why not explanations, and those all relate to the algorithmic techniques that I showed you before. Now, this means that we have to go to people and ask them what they want. This is not something that you just do, behind your computer. And this is what is central in the field called human-computer interaction. So I've been working in this field, human-computer interaction, which is a specific multidisciplinary field also involving computer science. And what we study there is how people interact with technologies. And that's very broad, I know. Technologies can be AI, for example. And so that's why human-computer interaction is actually the perfect field to study how can we design tailored explanations for a specific audience in a specific context. And also important is, how do these explanations affect people's behavior? Because that's in the end what we want to do. We want to know whether they improve, for example, in a specific task, whether it improves their understanding, whether they understand the explanation in the first place, right? So in general, what you need to understand here is explaining artificial intelligence is as much as a design challenge as it is an algorithmic challenge. It's not just about tackling algorithms with more algorithms. It's also about designing those explanations to what people need, how they understand it, and their specific contexts, right? And by the way, Cherry is just paraphrasing two very well-known researchers here. Now, an important question that I've not covered yet is, what should these explanations look like? Because they can be textual, maybe you can listen to them, or maybe you can see them, and they are visual. And so that's what I did. And someone will be very happy, because now I will be talking about visualizations. Yes. Shirin, come in. Interactive visualizations, what is that? So the rest of the talk, I'll just be presenting all the work that I did. There's 5 studies. And as you can see, there's different solutions that I applied: visual analytics, justification, control. I will explain what that means. But first, I want to tell you what visualization means again. Visualization does not mean we are going to work with diagrams or drawings of the inner workings of a model. That's not what I'm talking about. I'm talking about data visualization. And you already know this is not new. We all know bar charts and line graphs, and maybe you also know these disgusting pie charts in Excel. That's the visualizations that I'm talking about. Good. 3 general approaches. Visual analytics, let's start there. What we learned before is that we need to specify what someone needs. I mean, there's different groups. There's data experts, AI experts. They need very elaborate tools. And one of those tools could be visual analytics. In the word, you just hear visualize something, analyze something visually, right? So visual analytics means data analysis with highly interactive visualizations, typically in a dashboard. So, I mean, you've been getting dizzy because I was a bit too fast here, but this is an example of a visual analytics dashboard. So you see there's a lot of interactivity, a lot of visual components, and you can select stuff and get more details and click things away, etc. So quite complex, but still simple, actually, because this is just one visualization. And visual analytics typically involves multiple visualizations. So I'll shortly show you some examples. But you kind of get the idea. This is probably something for data experts and AI experts. This is not something you will come across on Twitter. So let's have a look at the first study. In the first study, I'll have to give a short introduction, because before I've been telling you that there's lots of AI models, and all these models, can be explained in different ways, and we have to take into account to whom we are explaining them, and also in what context. So each time I'm talking about my research, I will answer these questions. And so in this first study, I was actually interested in what exists out there, what kind of visual explanations exist, specifically in healthcare, but doesn't matter for whom, and it doesn't really matter which model. So just what exists out there. And to answer that question, I conducted a so-called systematic review. So what is that? You start with a search query. I mean, it's over there. It's a big search query with lots of words. And you just add them in some kind of search engine, and then you collect papers, and in the end, you classify all these papers, and you write a nice story. So that's what I did. Simple, right? Not so simple. It takes a lot of work to do this. First, the search query. I mean, you see, it's pretty elaborate. And the challenge here is that if it's too broad, you get thousands of papers. I mean, 10,000s or millions of papers. If you make it too narrow, you just get 10, and then you miss all the interesting stuff. So tweaking it until you get 2,000 papers, okay, that's feasible. Then we needed to filter all these papers based on their abstracts, so the summaries of the papers. So it's just like a paragraph or something. And then in the end, we got about 300 papers that were left that seemed interesting. And then I had to read all those papers. Every paper is about 20 pages, times 300. I have to see which ones are interesting. And once you have those 80-something papers, you need to analyze all of them. And I mean, this is such a nice, quick process, right? So that's why I had this smiley-shaped curve here. And especially the last part with the big table. I'm talking about hundreds of rows and hundreds of columns, and then you have to decide where to put the X's. Lovely, really lovely. What did I learn from all this work? Because this takes weeks of, full-time work. It turns out that in healthcare, there are 4 general approaches to explain with visualizations AI models in general. Visualization, interaction, control, direct explanation. Let's just have a quick look. I'm going to bombard you with examples and visuals. You don't have to understand all of them. I will just explain what it means. Visualization means we are going to visualize the outcomes of the model. So depending on what kind of model you have, you can just visualize it in a lot of ways. But there's typical patterns that you start to see. For example, if you have a so-called clustering algorithm, the AI model is called clustering, then you typically have these all these dots there in the left upper corner that get colors, and depending on the cluster, they get the same color, and you start to see those patterns. Then there is interaction. Interaction means we are interacting with the visualization. Like you saw before, we can ask for more details, filter, reconfigure, ask for a different type of visualization. We can select different data points. We can even connect different visualizations. I mean, there's plenty of stuff, and we can even combine all these techniques. And this helps us to see how models behave, and also how the data underlying these models, actually what it looks like. So all sorts of insights that we can obtain with this. Then there is control. Control means we are controlling the AI model underneath this whole system. It means that we can change specific parameters and see how the model changes and what it looks like. And then there's visual analytics systems that allow you to tweak these parameters in a specific window, and then afterwards they update the visualization. And other ones are tightly integrating it, so that means they just show you the visualization, and you can interact with this visualization directly change the model and immediately see what changes. So there's like a whole spectrum of solutions here. And then finally, there is direct visual explanations. These are visualizations related to what I showed you before. Feature importance, for example. Remember the tweets from before? We can visualize those numbers in different kinds of ways. And we can even visualize what the model is doing, like exactly, like just show me what it does. But this is all quite complicated. So the main takeaway of the study is that, as you probably guessed from the visuals, there is little support for AI novices, people who don't know anything about AI. This is all very complex and typically for data experts and AI experts. And another thing that I found is that all these visual analytics systems typically do not really allow a lot of control over the model. And there's not a lot of direct visual explanations. So let's go to the second study related to visual analytics. So in this study, I created a visual analytics system myself. It's actually a very simple system, typically for data experts and AI experts, as we saw before. It's a linear regression. And this was done in the context of agri-food. So it's like agriculture and food together. So let me just show you what it looked like. You saw the demo before. It's the thing that made you dizzy. These are the stills, and now you can see, oh, it's just like a line, and the line shows the price evolution of different products in different countries. And you also maybe see that there's this extra part that's the prediction of the price. And then there is also these different colored bands. That's the uncertainty in the model. So the model is not really sure what the price is going to be. So there's all sorts of things that you can see here, and what I wanted to do was to do interviews with people to see how they perceived these things that I made. The question that I had specifically was, how does this visualization and then the uncertainty that you saw affect people's trust and understanding of the model? So there is some kind of prediction model in the background apparently, but I wasn't telling people what it was, and I tried to see whether they would trust it or understand it just based on the visualizations that I made. And to do this, I conducted interviews with 11 people. I guided them through several scenarios, different settings. For example, first, just a prediction and prediction with uncertainty, and then some information about the past, with a comparison of two countries as well, same settings, so 8 scenarios overall. Okay, I led them through all these scenarios. What I wanted to do was to see how they perceived this system, right? So again, we have a nice smiley curve. We had a visual analytics system that I had to create. And then in the end, we have this nice diagram with lots of arrows and colors, and cool. It's not that easy. Let me tell you a bit about what I did in the background. So I had these interviews, and I recorded them. We had about 14 hours of recording. I guess it was even 16, but I was too lazy to check the exact number. Then I had to transcribe all those interviews. That is exactly what you think it means. It means listening, pause, type, play, listening, pause, type, yes. Until I had 120 pages of text. And all those pages I had to analyze. So how did I analyze it? I did a so-called thematic analysis. Thematic analysis means I'm just looking for patterns in the text. What are people saying? Do they say the same things or not? And then once I had these patterns, I mean, those are the 4 big blocks that you see, usability, etc. I needed to connect those themes, like how do they interrelate, such that I could make a nice story in the end. And so, again, nice smiley curve, a lot of work, and I was smiling, especially when it was done. But let me tell you a bit about the results, which is actually more interesting than me complaining. We have 4 different themes. Some things that were related to usability, things that were related to usefulness and what people needed, model understanding, and then in the end, trust. What you probably want to know here is the relation between all these things and trust, because that was the main question here. So the main takeaway here is that this usefulness and the needs that people have can directly and also indirectly affect people's trust in the system. So, for example, there is, does this pointer actually work? I've never, oh, I have. It does work. So let's, for example, look at this example here. You have usefulness of the visual components. Some people found the uncertainty that they saw very useful, and they saw, oh, there is uncertainty, cool, I will immediately trust the system more, because there is uncertainty present. Cool, that's a direct effect. But then, for some people, this uncertainty was useful, but it was useful because it allowed them to understand the algorithmic level, the model on an algorithmic level. So this means they saw the uncertainty, and apparently it helped them to better understand what this model was doing. And some people even just guessed the model because they recognized it. And it was this understanding that led to more trust. So this is an indirect effect through this model understanding. Other takeaways, people had different levels of experience with AI. People with low levels, they found it quite hard to understand this uncertainty. I mean, they didn't really understand it completely. People with high levels here did find it very useful. So all these things that you saw helped them to better understand how the model was reasoning and working. Cool. And people with high levels of experience also needed more control. So they were like, oh, I want to change this model, and I want to change specific parameters, etc. So cool. And then the final takeaway is, that was kind of fun actually for me in the background, because in each of these scenarios, I was also measuring people's trust, like with measurable numbers, right? And so you can plot them, and then you see this nice evolution and the curves. And what was cool here is that, I mean, they're all over the place, so everyone had a completely different story and a different evolution in trusts. And what's also cool is that even people with similar levels of experience, for example, the H's are high experience, some had low experience levels, and some had high trust levels. So even the experience that people have with AI is apparently not enough to have like the same kind of evolution. So that was really fascinating, and yeah, I agree. But let's go on. What I want to talk about now is justification and control. And actually this whole story is a lot easier, so you already had the hard part, yay. Why? Because actually these three studies are very similar, so it's always a very similar setup. In specific, what I was doing here is checking how I could explain a specific recommendation model to teenagers, so AI novices. They don't have any experience with AI in the sense of the mathematics. And I was doing this in the context of education. So in specific, I used a platform that I made a couple of years ago called Whiskey. What this does is people can just choose a specific topic, and then they can make multiple choice exercises, and they can immediately see whether their answer was right or wrong. So that's cool. But what's interesting here is that in the background, the system is keeping track of how good people are, and is thus like recommending different exercises to them based on that level. So actually, Whiskey is also a kind of black box, a recommendation system. Just like the tweets from before, but now with exercises. So how it worked was, I'm estimating the mastery level of different students, and then based on that mastery level, I will construct a different kind of exercise series with a specific difficulty that is hopefully like good for you, like what you need. So that was the general setup, and I did 3 different experiments with this setup. The first one is about justification. What does that mean? Justification means that we're providing simple insights in AI outcomes without like overloading anyone with all the technical details. So just a very simple takeaway, one insight. Typically something we would do for AI novices, such as teenagers. So in the general scheme, it looked a bit like this. So this is a scheme from before. Once we had these exercises that were recommended, we said, this is recommended because, and then we added something in the because. What we added was this. So this is in Dutch, but I mean, I will translate. There were 2 parts here in this explanation. There was a textual part that said, oh, I am recommending this because it matches your mastery level, and also similar students needed X attempts. And then the second part is a visualization of those attempts. So in this case, you see, oh, this is a bar chart, and similar students typically needed 1 attempt to solve this exercise. So that means probably it's not so hard, because 1 guess and they have it correct. Now, Also, I just wanted to give you a glimpse of what happened in the background. We didn't just come up with this design like in 5 minutes. We applied so-called user-centered design, which means that we have different iterations of the design, and each time we go to teenagers, ask them what they think about it, and then see whether they understand it, whether it's, fulfills their needs, etc., etc. And what we found here is that teenagers weren't really interested in a tutorial with full transparency over the model. They just wanted one simple screen, one simple visualization. That's the visualization that I showed you before. And again, we are researchers, so we're not just designing something, we also want to know what it does. And our question here was, how do these visual explanations affect teenagers' trust in the recommender system? So how did we do that? Actually, we tested this together with 2 other designs. So first, a placebo explanation. Placebo is just this fancy word for fake. So the explanation was, we are recommending this because our algorithm decided so. That's not really giving you like any insights in why or how it worked, right? So it's like a fake explanation. And then we also had this design without any explanation. So we wanted to compare these 3 different designs. And we did this in a so-called randomized controlled experiment. Again, that's a very hard word to just say there are different groups. A group with people who only see real explanations, a group with people who only see placebo explanations, and then a group of teenagers who see no explanations. And so we have these 37 teenagers who participated in our experiments. We just put them in one of these groups randomly, right? That's what a randomized control experiment is. So this means teenagers were using our platform, and then they saw one of these 3 things, and then in the end, we asked them a questionnaire about trust. Again, you don't have to read everything here. I just wanted to show you this because measuring trust is very complicated, and we did this in different ways. The first way was 1 question. I trust whiskey to recommend me maths exercises. Just say on a scale from 1 to 7 whether you agree. Just 1 question. And then we had all these other questions. You don't have to read all of them, but they are capturing other trust-related concepts, such as competence, benevolence, integrity, intention to return, perceived transparency. And then we combined all these answers because they're all numbers in the background, and we just, average and those kind of things. And that is what we call multidimensional trust. So just keep in mind that with these 2 trust measurements. Let me show you what we found. First, the group with the fake explanations. We didn't see any changes in trust when we compared them to people without explanations. So that's good, right? It means that teenagers were not misled by these extra things that they saw to trust it more. I mean, they basically saw the same thing. So that's good. That's why we added the placebo explanations. But then, the really interesting thing, the real explanations. What we found there is pretty interesting. If we look at the trust measurement with 1 question, I trust whiskey, there was no difference in trust. But when we looked at all these questions and combined them, then we found an increase. So this is interesting. It means that when you ask a single question and you just say, answer from 1 to 7, teenagers were not inclined to change from 5 to 6 or something. But when we checked more fine-grained, we did all these extra measurements, then we did see a slight bump. So that's cool, because this suggests that the explanations that we made here can increase initial trust, but maybe they're not the most important factor. Maybe those teenagers were more concerned about the design of the website, let's say, whether it looked pretty. Let's now check control. There's 2 studies, and control in general, what does that mean? I already talked about this. Control over the AI model to see what it's doing. We are trying to involve people in the decision process by allowing them to steer the model, changing some parameters, whatever. In the grand scheme of things, the scheme from before, again, just check the right side here. We recommended them specific exercise series, and with the control, we allowed them to change the difficulty level. So we recommended, for example, here's a difficult series, and then they could change it. They could say, no, maybe I want an easier exercise series, or the opposite, like maybe I want a harder exercise series, or maybe I'm happy and I don't want to change anything at all, okay? So that is what we did. And there's two different control mechanisms that we made, and I'm going to show the two of them. The first one looked like this. When those teenagers were solving the exercise, I mean, it was very fast, but it was the correct answer. They saw this slider. And with this slider, they could change what was happening in the background. Because in the background, the system was changing their mastery level. Remember, the system was checking whether they were any good. So in this case, the student had a correct answer. So the system would say, OK, your mastery level goes up because you had it correct. And then with this slider, the student could say, oh, you can bump it even more. You can give me harder exercises later on. Or no, just bump it a bit less because maybe I was lucky. I mean, next time I want easier exercises. So that's what the slider allowed them to do. And after this slider, they also saw a visualization because it's about visualizations in the end, right? What you see here is a line graph, very simple because it's teenagers. First, they see their master level before the series. It went up because they had a correct answer, and then it went up even more because they chose a hard exercise level with the slider. So, the natural question as a researcher, how does this control mechanism and the visualization affect teenagers' trust in the recommender system, like before? And again, we did a randomized controlled experiment. So there were different groups, 3 groups. A group without control, without visualization. A group with only the control, and then the group with control and the visualization. And again, we wanted to compare these different groups. We again used the questionnaires. Just wanted to show you this like before, but now we added extra questions and refined the questions from before. But what's most interesting here is, okay, all these teenagers were using the platform. What did it do, right? So in the group with teenagers who only had control but did not see the visualization, we found the following. Their trust did not change. They had control, but didn't affect their trust. But what was interesting is we also asked these open questions, so they could just like type whatever they wanted. Questions about their control and whether they trusted it, etc. And there we found that these teenagers were mentioning their own mastery level, and also that there was some kind of recommendation system, a lot more. And I mean, spectacularly more, like double the amount or something. So that was very interesting. Apparently, it did something with their reflection. Then we checked the visualization. Did the visualization do something different? And the answer is yes. Teenagers who saw the visualization after the control mechanism had higher trust levels. And again, quite spectacularly. That's 1 point on a scale from 1 to 7. So they, I think in general, bumped their trust from 5 to 6 or something. So that's quite a big change. And again, this is because they reported that they found the system more transparent. Probably because the visualization showed how the model was behaving, and because they saw this each time, they could also see how the model worked, I guess. And again, as before, they also reported a lot more like reflective remarks about the system here. So the conclusion here is that the control alone may not increase initial trust, but showing the impacts in the visualization can. Let's quickly go to the last study. The last study is quite similar. We also had something with a slider and something with a visualization, but we showed it on the same screen, and now we showed it before students were going to start an exercise series. So they chose a specific topic, and then we showed them this, and the slider allowed them to immediately choose an easy or a hard exercise series. And the visualization is actually a what-if explanation. That's something I mentioned before, but maybe you forgot. So what if means what will happen with your mastery level if you solve an exercise from this specific difficulty correctly. So you choose a specific difficulty. If you have it correct, then this will happen with your mastery level. And it will go up, of course, because you have it correctly. But you also see, if they make it very hard, then the change is bigger. You see, it's quite small on the big screen, but... And another thing that we did is the same slider, but then we added these extra motivational sentences. Sentences that said, I trust that you have the capacities to solve this exercise correctly. Maybe you can even make it a bit harder, something along those lines. Just keep in mind that we also had this in our experiment. And then we did another randomized controlled experiment. Yes, because we wanted to compare all these different designs. But we also did a lot more design iterations, both with teenagers and with teachers. And I quickly wanted to show you this because, again, we had a lot of interesting insights here. In the first design that we made, teachers were like, the explanations that you show are visually overwhelming and motivation is most important for students. Then we said, okay, let's simplify this a bit. We have the why explanation still. It is trying to explain why you get this exact recommendation. And then there's also this what-if explanation that shows the change in your mastery level. And we again showed this both to teachers and to students. And we found that the why explanations were found quite complex and more like suitable for adults, whereas the what-if explanations were found motivating by students. So that was good. So we said, okay, let's just drop the why explanation and focus on the what-if explanation. And then we showed this again to students, and they said, yeah, that's cool. We can see our progress. We like it. And also the sentences that I showed you before, they found them motivating. So that's why we call them motivational feedback. And so that's how we ended up with the final design here. And it was this design that we used in our randomized controlled experiment. And now we had 170 teenagers and 4 groups. So one group with nothing at all, no control, a group only with the control, and then a group with the motivational feedback and the what-if explanations. Okay? 4 different groups, so that means a lot of takeaways. And we measured trust again, yes, but we also measured other things. We also measured metacognition. That just means reflecting on your own level, for example. We also measured endurability, whether the teenagers were inclined to come back to the platform. We tracked learning motivation. Does whiskey motivate them to learn? And learning performance. Like, do these things help them to be better? What we found was very interesting. In all the 4 groups, there was no difference in trust. That's not what we expected. Metacognition, also no difference. Endurability, no difference. Motivation, no difference. Learning performance, also no difference. So that was a bummer. I mean, we spent months of design iterations with these teenagers, and we found basically not what we wanted. So my reaction was something like this. Exactly. I was kind of pissed off because we did a lot of work and was like, okay, this is interesting. But then, you know, once I calmed down, I was like, okay, maybe this is a good lesson. This shows what research is. Research is not about doing something and then finding what you want. It's also not finding what you want, because apparently reality is different. So that was a very important lesson. There was something that we did find, so there's Mr. Brain. We did find differences in how these teenagers were using the slider. So this is a bar chart, and it's just showing the different slider values, you know, from very easy to very hard. And the bars just show how many times they were chosen. What was interesting was the differences between the groups, so the control group, the what-if group, and the feedback group. The differences are a bit hard to see here, but so I plotted them here in these other visualizations. We see that the what-if explanations apparently lead to more values around the center and also at the difficult end, but actually a lot less at the easy end. And the same thing happened for people with feedback. So those what-if explanations and then the motivational feedback that people saw once they were using the slider apparently encouraged them to try harder exercises. Okay, that's a cool takeaway. We learned something there. But the main lesson from this whole last study is tailoring. We did a lot of work to tailor these designs to what teenagers needed, wanted, could understand, what teachers thought was most appropriate. And this is key to what we are trying to do in human-computer interaction. And with that, we are at the end of my presentation. No! Unfortunately, yes, but I mean, let me quickly recap what we've learned today, because I've been talking for a long time. First, AI models are like coffee machines. You put something in, something happens, something comes out. These coffee machines are often black boxes. We don't know what happens inside them, so we need tailored explanations. I propose to use interactive visualizations to format these explanations. And in specific, I had 3 different approaches: visual analytics, the very interactive complex visualizations, typically for data experts and AI experts; justification, very simple insights, typically for AI novices, such as teenagers; and control mechanisms that allow people to steer those models. This is just the tip of the iceberg. There's a lot more to unpack, a lot more findings, background material, so I warmly invite you to read the text. You can just download it for free on my website. The link is over there. I will give you a brochure in the end, and the link is still there, so you can use it. Even to the scary-looking people who are not into research, don't panic. I wrote a whole background introductory chapter that is accessible, I hope, to everyone. This is not in academic jargon. And I also added a lot of personal stories and photographs after each chapter. So hopefully that also inspires you. And so, the very, very final thing I want to say is I hope that you found this work inspiring, and I hope I have convinced you that these visualizations that I showed you are very powerful techniques to show what's really going on inside those black box models. Thank you very much.